Hello everyone. Let's start off with some sample diploma questions. So give them a go on your own. There's lots of them and some of them are tricky. So really important that you try these out before you see me go through them. So this first one, the potential difference between the anode and the cathode of a vacuum tube is 2 times 10 to the 2 volts. Free electrons originate from the cathode with negligible speed and move to the anode. The speed of the electrons as they arrive is. So this is one of those law of conservation of energy questions. So what they're talking about here is they're talking about the acceleration chamber. So in the acceleration chamber, we have our cathode, which is negative, and then our anode, which is positive. I'm just going to grab a new pen. This pen is dead. Okay. And our electrons originate here, and they fly over to the other side. So it says they have negligible speed here. So they just have electrical potential energy. Here they have kinetic energy. So it's just physics principle number 5. And our energy before equals our energy after. And we have EPE is equal to EK. So EPE is VQ and 1/2 mv squared. So we're trying to determine the speed. So 2 moves up there, mass moves down below, and we square root it, and we can find our speed. Okay. So I'll just plug it into the calculator to save a little bit of time. So they give us our voltage, and they say they're electrons, so we know the charge of it. Thompson did not, but we do know the charge of it. Okay. So it's going to be 2 times our voltage times our charge divided by the mass of the electron, which is 9.11 times 10 to the negative 31 on the bottom. And then remember to square root that, because you'll always get an answer bigger than the speed of light. And we get 8.38 times 10 to the 5. So 8.4, or times 10 to the 6. 1, 2, 3, 4, 5, 6, times 10 to the 6. So we get 8.4 times 10 to the 6. So A becomes the correct answer. Okay, this one, electron passes undeflected through a perpendicular electric and magnetic field with strengths of those. Determine the speed. So this is talking about the velocity selector region. So in the velocity selector region, they go through undeflected. So what that means is they pass through a magnetic field, and they're electrons. So I'd use my left hand here. The electrons go through. My magnetic field is into the page. It doesn't actually say that, I'm just giving an example. So my magnetic force is down, and then to make this work, we would need a positive plate on top and a negative plate on the bottom, and that would deflect the electrons up. So we get our Fe to equal our Fm. Fe is electric field times charge, and Fm is equal to QVB. Our charge always cancels out there, so it's going to be electric field divided by magnetic field. So our electric field is 2 times 10 to the 4 newtons per coulomb, and our magnetic field is 1 times 10 to the negative 2 teslas. So if we plug that into our calculator, 2 times 10 to the 4 divided by 1 times 10 to the negative 2, we get 6. 2 times 10 to the 6 as our answer. So that'll get us C as our answer. Okay, in a charge to mass experiment, it's found that electrons traveling at that speed are deflected in a circular path. Okay, so we want to find the charge to mass ratio for the experiment. So if they go in a circular path, that lets us know that we're using physics principle number 2. So what makes it move in a circle? Well, it's that magnetic force that makes it move in a circle. So this breaks down into mv squared over r. This breaks down into qvb. And one of those velocities cancels out. And we want a charge to mass ratio, so we have to put our mass down below. And then we'll move the b over to the other side. Okay, so our speed is 7 times 10 to the 6 meters per second. Our magnetic field is 1 times 10 to the negative 4 Teslas. And then our radius is 0.4 meters. Okay, so we're ready to plug that all in. So on top we have 7 times 10 to the 6. And then on the bottom we have 1 times 10 to the negative 4 and 0.4. So we get our charge to mass ratio is 1.75 times 10 to the 11, so 1.8 times 10 to the 11 is our charge to mass ratio. Okay, a magnetic field directed out of the page caused the cathode rays to move up in the screen. What is the arrangement of the electric plates that would cause them to return to the center? So you can see that our magnetic field deflected them upwards. So that means that our electric field would have to deflect them downwards. And their cathode rays, which you should know are electrons. Oh, sorry, it says out of the page. I drew that wrong. So it'd be circles or dots. It'd be out of the page. Would make it go upwards. Yeah, that makes sense. So if we want our electric force to go down, we need our positive plate to be on the bottom, which makes B the correct answer. One immediate result of the discovery of cathode ray particles was the theory of the atom that revised to the theory that hypothesized, was revised to a theory that hypothesized. So this took over Dalton's model, and the cathode ray particle showed us that the atom was not an indivisible sphere. Oh, sorry, I just read that wrong. One immediate result of the discovery of cathode ray particles was the theory that the atom was revised to a theory. So this is a theory that it revised to. And what Thompson found in his experiment is that there's these negatively charged particles, these electrons. So sorry, D is the correct answer. My bad. Two physics principles that must be used to determine. Oh, these guys go together. That's weird that this one's first. This should be second. Anyways, so this is a cyclotron question. A cyclotron is one type of particle accelerator that can be used to accelerate charged particles to very high energies. So this shows a little diagram. I'm not going to read this whole thing because I know how it works. But what happens is that when the electron crosses this gap here, it accelerates. I wish that mouse didn't skip like that. Let me try that again. So when it accelerates across this D gap, this D separation here, it accelerates, and then it travels in a circle, and then it accelerates across this gap, and then it travels in a circle, and then it accelerates across this gap, and then it travels in a circle, accelerates, circle, accelerates, circle. So one particular cyclotron is shown below. In this cyclotron, the charged particles are protons. Okay, that is key. The magnetic field strength is this, and the electric potential difference between the plates is that one particular proton has a speed of 5.6 times 10 to the 6 meters per second as it approaches a D separation. The radius of curvature of the proton after the D separation is. Okay, so this is a tough question. It's hard to figure out what they're saying in the question, but what it's saying here. So this is our D separation, like that. And then, so the proton accelerates across here, and then it'll go in a circular path, and then it'll accelerate across that D separation as well. So there's two parts to this question. The electron is moving, or sorry, the proton is moving, so it has kinetic energy here, right? But to make that proton accelerate, we would make this plate positive and this plate negative, so it would also have electric potential energy. And then as it goes here, it's just going to have kinetic because it's where it wants to be. So the first part of the question, we need to use the law of conservation of energy. We need to use physics principle number 5. Okay? Before we have kinetic energy and electrical potential energy, and then after we have kinetic energy. Okay, I'm just going to leave that there now. The second part of it is it goes into this curve. And anything that goes in a circle, we're going to use physics principle number 2. And that's where that magnetic field makes it curve. So this is mv squared over r. This is qvb. And one of our velocities cancels out. So in this question, they're asking for the radius of curvature. So they're asking for this right here. So I'm going to move that r up top, and then the qb down below. So we get mv over qb is equal to r. We know the mass of a proton. We know the charge of the proton. And the question tells us the magnetic field of the proton, right? What we don't know is we don't know the speed. And that's what we're going to use this for. We need to find the kinetic energy of the proton after. We need to find the speed of that proton after to help solve this question. So to break this down, this is going to be 1/2 mv squared before, and then vq. And that's going to equal 1/2 mv squared after. So let's look at what we have. So we have the mass of the proton. We have the speed of the proton as it enters a d gap. So we have that. We obviously have 1/2. We have the charge of the proton, mass of the proton. We're trying to find this here. We know 1/2. And do they give us the voltage? Yes, they give us the voltage here as 0.2 megavolts. So we have everything that we need for this equation to find our speed. So to rearrange this, we'd move the 2 up top, and then we'd move the mass down below, and then we'd have to square root it to find that V. So I'll plug in the numbers here. So 1/2 times the mass of the proton, and I just want to double check to make sure I throw in the right number for that mass of the proton. I think it's 1.67, but I need to find a data sheet. There's one. Just to double check. We don't use the proton that often, so yes, it is 1.67 times 10 to the negative 27 kilograms. And then this is our speed as we enter that D gap, which is 2.5 times 10 to the 6. They give us that in the question. Okay, and then our voltage is 0.2 megavolts, so mega is times 10 to the 6. So 0.2 times 10 to the 6 volts, and our charge is 1.6 times 10 to the negative 19 coulombs. So that's all the stuff inside the brackets. I'd have to multiply it by 2, divide it by 1.67 times 10 to the negative 27 kilograms, and then square root it. So I'm definitely going to do that on my on-screen calculator so you can see how I would type it in. So I'm going to do all that stuff inside the brackets here first. So I'm going to go 0.5 times 1.67 times 10 to the negative 27 times 2.5 times 10 to the 6, and do that all in brackets. And then I'm going to add on 0.2 times 10 to the 6 times 1.6 times 10 to the negative 19. And that's all the stuff inside of the brackets here. Did I square that speed? I did not square that speed. So let's insert a squared in there. That would have made it wrong. Cool. Yeah, I have trouble with this on-screen calculator because it just doesn't type nicely. Okay, I think that's all good. So that's all the stuff inside of the brackets. And then I'm going to multiply it by 2. I'm going to divide it by 1.67 times 10 to the negative 27. And I'm going to square root my answer. And I get that, 1, 2, 2, 3, 4, 5, 6. Yeah, 6.67 times 10 to the 6 is a pretty reasonable answer. So now that we have that speed, we can plug it into this here. So we'll go 1.67 times 10 to the negative 27 times our answer from before, divided by our magnetic field, and they tell us that magnetic field is 0.863. And nothing is square rooted there, so we're good. So we're going to take that, we're going to multiply it by the 1.67 times 10 to the negative 27. What's going on here? Oops. Sorry, that's not going to give us a reasonable answer. Did I rearrange this correctly? MV, and then I threw QB underneath. Oh, I forgot the charge here. I erased it with my finger. That's why. So yeah, I was like, that's not going to give us a reasonable answer because it should be in the centimeters. So sorry, I need 1.6 times 10 to the negative 27. No, 1.6 times 10 to the negative 19 coulombs. Yeah, I erased it with my finger there, so that's why it wasn't there. There we go. So that's the top, and then I'm going to divide it by 0.863 and multiply that by 1.6 times 10 to the negative 19. And I get, yeah, about 8 centimeters. So my answer is going to be 8.07 times 10 to the negative 2 meters. Yeah, 8.07 times 10 to the negative 2, so 80272 would be my answer. And then for the other question that's asking about the physics principles, well, I used 2 and 5 and in any order, and those are the only 2 answers that would work with that one. So you can see I used physics principle 5 and I used physics principle 2. Okay? Whew, that was a lot of stuff, but luckily the lesson today is super short with Rutherford. Okay, so now we're gonna look at a new model, the Rutherford model, which most people are pretty familiar with. It's like the favorite for sketching the atom, but it actually works horribly. So curriculum, explain qualitatively the significance of the results of the Rutherford scattering experiment, and in terms of size, scientists' understanding of relative size and mass of the nucleus, and explain qualitatively how the emission of EMR by an accelerating charged particle invalidates a classical model. Okay, so the Thompson model of the atom, we call the plum pudding or the raisin bun model, which is like a very outdated name because most people don't know what plum pudding is. Plum pudding is actually like a cake with plums in it. And then raisin bun, disgusting. Like it should be called the chocolate chip cookie, the pepperoni pizza model. Like we need to update these nicknames, but you'll see it as these plum pudding or the raisin bun model. Okay, so the electrons are embedded inside the atom like raisins in a bun, disgusting. And there isn't protons. Remember that Thompson only created a model for what he found, and he found those cathode rays, and those cathode rays are electrons. Right? There's no positive charges. There's no protons. But he knew that you couldn't just have negative charges. You needed something to balance it out. So the charges were balanced out with an equal amount of positiveness. Again, I'm doing air quotes because positiveness isn't really a word. So the positiveness were not separate particles, but a cloud that was dispersed diffusely. So this is like a cloud of positiveness. And the positive charge could be thought of as the bun in the raisin bun, right? So the whole thing was positive. Cool, that's his model. So Ernest Rutherford did some experiments. He believed Thompson's model and he wanted to do some tests. So just a little heads up that the Rutherford who supplies you with your scholarship for university is not the same as Ernest Rutherford. Alexander Rutherford is over here, and he was Alberta's first prime minister or premier, and Minister of Education. And this is Ernest Rutherford, who I think is like British and has nothing to do with your scholarships. There we go. So, alpha particles. So an alpha particle we've talked about before, and they are high energy emissions from certain types of radioactive substances like radium. So if you want to get alpha particles, you just get a radium, and radium shoots off alpha particles all the time. So an alpha particle is identical to an electron-stripped helium nucleus. So helium has 2 protons and 2 neutrons, right? And a helium nucleus would also have 2 electrons as well. So what an alpha particle is, well, we get rid of those electrons. It doesn't really change the mass or anything because electrons have such a small mass, and that's what alpha particles are. They're just a helium nucleus. So Rutherford wanted to use these particles as a high-speed bullet to penetrate Thomson's atom. And alpha particles aren't able to penetrate things really well, so these are different particles that you can shoot off things. Alpha particles will be stopped by a sheet of paper. So alpha particles, so Rutherford in his experiment, he used gold foil, and you can stretch gold foil really, really thin to a few atoms thin, which is pretty amazing, so that the alpha particles can go through them. So what he did was he aimed alpha particles at a thin sheet of gold foil and placed a detector screen behind it. So he was not trying to do anything other than figure out more about Thomson's atom. So by measuring the scattering of the alpha particles from a straight line path, Rutherford hoped to deduce a statistical calculation of the density of electrons in Thomson's atom model. So he just wanted to find what the density of those electrons were. So I can show you a little demo here of what happens with his experiments. I'm going to show you a little, it's not an analogy, but just like a little demo to show you what happened. Just setting it up. Okay. So this is the atom, right? So Rutherford, Thomson, Dalton, none of these guys could see inside the atom. They didn't know what it looked like. All that they had was experimental evidence, and they had to guess what it looked like based on the evidence that they had. It's kind of like that Love is Blind show on Netflix. I don't know if you've watched it, but you don't know what they look like. You're just trying to guess what they're like from their personality. So Rutherford shot alpha particles at it. So to symbolize the alpha particles, I have these marbles here. So when Rutherford shot the alpha particles at the atom, so I'm going to throw them at the atom. This is my detector screen behind here. He expected those alpha particles to pass right through, and that's what they did, right? He shot them at it, and they passed right through. Every time he shot it, it would pass right through, and that's exactly what he was expecting. But every so often, when he shot it at it, he'd get them to bounce off at weird angles. Weird. That bounced off at weird angles. And about very, very few, but every so often, he could get it to, trying to get it to bounce, there we go, to bounce straight back, right? So most of the alpha particles passed right through. Some of them passed at different angles, like that. But once in a blue moon, he'd get it to bounce backwards, which was crazy. So I know you don't understand how crazy it is. So in this experiment, most of the alpha particles did pass straight through. Some deflected at small angles, as were expected if the alpha particles collided with the electrons or were attracted to the electrons. But a very big surprise is that some of the alpha particles, so about 1 in 8,000, deflected at very large angles, more than 90 degrees. So he has a very famous quote in what he says: "It was almost as if you fired a 15-inch shotgun shell, so a 15-inch shell, at a piece of tissue paper, and it bounced back and hit you." That's what his experiment was to him. He was expecting all of them to just pass through, but they didn't. They bounced back. So there must be something going in there. And this led him to the new model where the protons and neutrons were concentrated in a dense nucleus and the electrons circled around it. So I have a simulation here to show that. So this is what Rutherford expected. He expected the Thompson plum pudding model was correct, and he would shoot these alpha particles through, and judging by how much energy they lost, he could figure out the density of electrons in this sort of cloud of diffuse positiveness. But he expected all of them to pass right through. That's not what happened. He got them to bounce off at weird angles, so he created a new model of the atom, where the nucleus is this dense center. Most of the atom is empty space, and the electrons orbited around it. So if I shoot the alpha particles at this model, right, look, most of the alpha particles pass right through, just like he saw. Some of them deflect at small angles, but it might take a little bit. But what we'll see is that once in a blue moon, we actually get an alpha particle to bounce straight backwards. We gotta wait for it to happen. Come on. I got one earlier when I was testing this out. It takes a while because they're so small that it needs to hit it dead on to actually get it to bounce straight backwards. This almost reminds me of The Office when they're trying to get the screensaver to bounce right in the corner. Come on. I don't want to wait any longer. This is this new model of the atom. So dense nucleus, protons and neutrons in there, electrons orbit around, and most of the stuff passes straight through because it's mostly empty space. So Rutherford interpreted this as meaning the atom was only mostly empty space with an extremely small nucleus and the electrons orbit around it. But electrons are interpreted as circling the nucleus, which means they're undergoing centripetal acceleration, right? We learned earlier that if you have an accelerating charged particle, well, what happens to it? If I have there are two ways to accelerate a charged particle. If I accelerate an electron across a plate like this, I create EMR, right? So if I have this positiveness and these electrons orbiting around and they're going around, well, they're accelerating, right? Fc is equal to Fe here. And we would get EMR emitting off of there. Okay. EMR is energy. Right now they have kinetic energy as they go around. So if they lose energy in the form of EMR, well, something's going to happen to the atom, right? So this makes this model very invalid because accelerating charged particles must emit EMR. And if they are emitting EMR, well, let's take a look at what would happen. So if we shot stuff at, this is the Dalton, the billiard ball model, right? It's impenetrable. It doesn't go in. You can shoot stuff at the Thompson model, the plum pudding model, and it goes straight through. And then if we try Thompson's, let's try that again. No, this is Thompson, Rutherford model, Thompson, Rutherford. Look at this. Maybe let's, is there a slow motion? Yeah, let's do a slow motion. But anytime you try to model out the Rutherford model, well, if it's accelerating, this is the electron, it's losing EMR and is going to spiral into the nucleus, and if an electron spirals into the nucleus, it would cause it to explode. So we are made of atoms, we are made of protons and electrons, and we don't explode all the time. So something is happening here, and this model doesn't work very well. So as electrons emit EMR, they would lose energy, and they would spiral into the nucleus, which makes this model invalid, right? So remember that models aren't correct. Dalton's model works in chemistry in lots of situations, but it's not correct. Thompson's model had the electrons in there, which is awesome, but it's not correct. Rutherford's model was able to explain his experiment with the dense nucleus, which is really good, but the fact that electrons would spiral into the nucleus makes it invalid. So this model doesn't work very well, and that's where we're going to leave it right now. So very little homework with this. So do these 3 questions, and they're super easy, and that is all. Thanks for watching.